All right, it's time to talk about cooling curves. So a cooling curve is exothermic. Energy is being released. All right, so and it looks like this. So the general trend is going down, okay? So you can see the temperature as the general trend is going down as time increases. So for a cooling curve, we're going to start with a gas when we have all of the pieces. And then a gas to a liquid, it condenses, and then a liquid cools down, and then a liquid goes to a solid, it freezes, and then the solid cools down. So again, we have a gas being cooled, then the gas condenses, changes to a liquid, and then the liquid is being cooled. And then the liquid freezes, it changes to a solid, and then the solid is being cooled. So this is literally just the opposite of a heating curve. So up here at the top, in a heating curve, we have the gas being heated up. So in a cooling curve, we're starting with the gas, but it's cooling down. So the general trend, it looks the same, it's just reversed, okay? Same states of matter. So when it is the slanted piece, it is one single state of matter, gas, then liquid, then solid. And when it is flat, there is a change of state. All right, so let's look at this again. The heat of fusion or heat of freezing and the heat of vaporization or the heat of condensation. You could call it either. But you can see again that the distance between B and C for the heat of vaporization is greater than the distance here for the heat of fusion. So there is more energy released as a substance changes from a gas to a liquid than there is released when a substance changes from a liquid to a solid. All right, let's look at more. So temperature is average kinetic energy. So when the temperature changes, the kinetic energy changes. So we have kinetic energy decreasing here because the temperature is decreasing. We have kinetic energy decreasing here because the temperature is decreasing. And we have kinetic energy decreasing here because the temperature is decreasing. So if the temperature is constant, the kinetic energy is constant. So we have kinetic energy constant here and kinetic energy constant here because there is no change in temperature. What about potential? Well, let's see. Remember, temperature is average kinetic energy. If the temperature is changing, the kinetic is changing. So potential is constant. Remember, it's either kinetic or potential changing. So the potential is constant because the temperature is changing. The potential is constant because the temperature, and thus kinetic, is changing. And the potential is constant because the kinetic is changing because the temperature is changing. And then if the temperature is constant, the kinetic energy is constant, and the potential is changing. So no temperature change, that means potential is decreasing. No temperature change, that means potential is decreasing. Okay, so again, in a cooling curve, we have a gas condensing, gas cooling, gas changing to a liquid, condensing, liquid cooling, liquid changing to a solid, freezing, solid cooling. So where we have a constant temperature, we're forming stronger intermolecular forces. So energy is being released. That's what's happening during a phase change. And this point right here, condensation point or boiling point, and this right here would be freezing point or melting point. It's the same temperature. We'll just call it one or the other based on the graph. Okay, so again, you can see that the kinetic energy over the span of the curve is decreasing, as is the potential. Okay, so again, the gas starts to condense right here at Q, completes condensing at R. The liquid starts freezing at S, and completes freezing at T. So how can I tell this substance is water? Well, if I go across on this flat part where I know it's between a solid and a liquid, it's at 0. And that is, in fact, the freezing point or melting point of water. So how can I tell this is not water? Well, I look at where it's flat and I go across and it says 80 degrees Celsius. Well, that is neither the boiling point nor the freezing point of water. So this is definitely not water. All right, so again, this segment right here, potential is staying the same, kinetic is decreasing, the gas is cooling. The kinetic is staying the same, constant, the potential is decreasing, the gas is condensing. So we're getting gas to liquid right here. All liquid at this point. The liquid is cooling, kinetic energy is decreasing, potential is staying the same. Right here, now we have this was all liquid. Now the liquid is changing to a solid. The kinetic energy is constant. The potential is decreasing. This is freezing. Now all a solid at this point. The potential is staying the same. The kinetic is decreasing. The solid is cooling. So a substance begins to condense. What happens to the potential and the kinetic energy? Well, the potential decreases, but the kinetic stays the same because while it's condensing, the temperature doesn't change. Temperature, do you remember what it is? What kind of energy? Kinetic, right? It's average kinetic energy, a measure of the average kinetic energy. How does the speed of and space between water molecules compare in a solid versus in a liquid? Well, the molecules move faster and are more spread out in a liquid, so that means the molecules are moving slower and are closer together in a solid. And there you have it. That is cooling curves. I hope you learned something new today.